Okay, so today we speak about clusters and clustering and different ways of testing for that. And I'll start with some remarks about the concept and the different types of approaches. Then we'll focus on three specific test approaches. The Quadrat counts, which are some of the oldest methods used in the literature. Scan statistics, which are pretty much the standard in applied public health and epidemiology, particularly because of the software SAT scan. And then distance-based statistics, which are a little bit more involved and provide the first connection to the actual processes, the types of spatial processes that we then will try to model and estimate. So basically what we're interested in is detecting patterns that are different from spatial randomness. The benchmark, the point of departure, is always complete spatial randomness. And as we saw last time, in and of itself, that's not really that interesting. And in fact, very few processes in the world are completely spatially random. But it's a benchmark. It's something to compare to and then decide whether we have regular patterns or clustered patterns. And it's very important to make the distinction between clustering as a characteristic of the complete pattern, or as we call it, as a global characteristic, and a cluster, which is a specific location, and which we call a local characteristic. So when you establish through one of these test statistics that there is clustering in the data, in the points that you observe, there is no way for you to tell where the clusters are. It is a characteristic of the total global pattern. So in some sense, it's a characteristic of the process that generates the whole pattern. But it is not a characteristic of specific locations. So it's more interesting or more relevant, if you wish, if you're interested in fitting models, because it tells you the kind of models you have to start thinking about, whether it's a model for clustering or a model for inhibition or regular patterns. But it's not that interesting from a policy perspective if you want to locate what are the hotspots of crime or what are the locations where cancers are elevated or things like that. That is for the second item, where you want to find, by means of statistical techniques, not just that the pattern is different from randomness, but also where the specific clusters are. So here we try to get a local measure that tells us, okay, in these two counties, the rate of this disease is elevated more so than it would be under a random pattern. And so that's very location specific. And the approaches that we take for one do not work for the other. So very important to keep in mind when you do, and this is also for your assignment, when you do tests for clustering, you cannot establish where the clusters are. Okay. That's where the statistics stop and the imagination begins. And what all this is about is to rule out as much imagination as possible and be able to assess quantitatively with some probability level whether or not these patterns are more clustered or more regular than they would be randomly, or where the clusters are, again, with a p-value, as we'll see later on. So clustering is about characteristic of the complete pattern, and we're primarily interested in finding out deviations from complete spatial randomness. And there are, roughly speaking, three major ways to approach this. And two of these we'll cover today, and then one we'll leave for the next time. One is to focus, and they all focus on different characteristics of the point pattern. The first one takes an obvious characteristic, namely the intensity of the point pattern. And remember, the intensity is the number of events per area. So under spatial randomness, we can figure out what the intensity of the process should be. We already know it's going to be uniform. So in so many words, pretty much no matter where you are in the pattern, you should find roughly the same number of events per areal unit. And that leads to a set of statistics which are called quadrat counts, which are nothing but counting the number of events in a quadrat. And a quadrat is just a geometric shape, typically a square or a circle or a rectangle or something like that. That's one way to approach it. The second way to approach this is that under spatial randomness, the points follow the locations of the points of the events, follow a particular distribution. And that distribution has certain characteristics about the distances between the events. And so once you can establish how the distances between events should behave under spatial randomness, then you can also find out whether the pattern that you're looking at is different from spatial randomness. And this is the basis for the distance-based statistics. And there are literally hundreds of these, but we'll focus on a couple that are called more refined distance-based statistics in the literature. And they're basically cumulative distribution functions, as we'll see, and they're the G, F, and the J function. And they're based on distances between events or distances from control points to events. And again, the rationale is the same. Under spatial randomness, we know how these distances behave, so that gives us a benchmark to compare what our specific statistic that we observe for the points at hand to the benchmark. And then the third set of statistics, which we won't talk about today, focuses on the second order moment. And this is a little bit more mathematical, a little bit more abstract. The intensity, as we saw, or maybe we talked about a little bit, is like a mean, like an average of a distribution. It's a first moment that characterizes the distribution. The second moment is more like a variance or a covariance between the locations of the points. So the K function and its cousin, the L function, are really based on the second order moment. It's a characteristic not of the average of the mean tendency, but about the variability around that mean tendency. And again, same thing, under complete spatial randomness, we have a good idea how that second moment should behave, and we can therefore construct statistics that allow us to assess whether what we observe in the point pattern at hand follows complete spatial randomness or not. So that's always the same rationale that we follow. So these are tests for clustering for the complete pattern at hand. And the way you can think about it, it's a single number or a single statistic that summarizes the full characteristics of all the points. Whereas the second category of tests, we're interested in finding the actual locations. So typically, we're interested in clusters of high values. Every once in a while, we're also interested in clusters of low values, but it's actually very easy to go from one to the other. The rationale is a little bit different because we're not interested in the pattern of all the points as such, but we want to find, if you wish, those points that are different. Those collections of points that deviate from the pattern and specifically where they are. So we're interested in finding out locations where, say, we have elevated counts of events. And you can think of statistics that use a similar kind of rationale in that they take a circle or a square and they move them over the point pattern, and they pick out the locations where there are more points than there should be. Not just on average, as in the case of the clustering statistics, but specifically location specific. We find here there are more events than there should be, and we can attach a p-value to that, and by means of that p-value we can reject the null hypothesis of randomness in favor of an alternative of a cluster in that specific location. And a family of statistics that do this are called scan statistics. And scan statistics are very similar to quadrat counts. In fact, you can think of them as kind of an evolution of the quadrat count, in that it's also based on counting events in a particular geometric shape. Typically a circle or a square, sometimes an ellipse, So essentially, you draw a lot of these circles over the points, and you count how many points fall into the circle, and then you have a statistical way to assess what is the probability that this number of points fall in the circle. And if that probability is small enough, you reject a no, and you have identified a cluster. That's the basic rationale. And some of these go back to what is called the geographical analysis machine, or GAN, which is an exploratory technique. There is a similar technique that's used a lot in criminology. It's called STAC, Space-Time Analysis of Crime, and it is in the CrimeStat package. We won't actually use it in the lab, but you're free to explore it. And then the one that is the most accepted today, in fact, if there is such a thing as a standard, this is the standard for testing for clustering in public health and criminology. That's the Kuldorff scan statistic implemented in the SAT-SCAN software. Okay, let's start with the Quadrat counts and the principle behind it. It's actually very simple. Okay, you have a point pattern, and if the point pattern is random, then no matter where you put a square, you should have roughly the same number of points. So what we're going to do is do a goodness of fit test. In that, we're going to create a grid over the points of a bunch of squares or rectangles, and count in each of these grids how many points there are. And we'll compare that to how many points should be there on average. And on average, if the point pattern is really truly random, then each area should have an equal number of points. So if you have, say, 100 points, and you have 25 squares, then each of these squares should have 4 points on average. Right? So if it doesn't, then there's a deviation from this average. How large is that deviation? That we can test with a simple chi-square test of goodness of fit. And that's basically what a Quadrat count test does. It takes the expected count in each subregion, and the subregion is these squares that we have. So on average, if we have n subregions or n squares and n total events in the point pattern, so we had 100 events, 25 subregion, each subregion on average should have 4 events. So in this case, the mean of n should be 4. So then for each of the cells, we take the actual number observed of events, n of I, we subtract the mean, we take the square and divide by the mean, and sum this up over all the cells, m cells, and that is your classic chi-square measure of goodness of fit. And we lose 1 degree of freedom. Why do we lose 1 degree of freedom? You estimate the mean. Anytime you estimate a parameter, you lose a degree of freedom. So that's why this is a chi-square with m, the number of cells, minus 1 for this mean that we estimated from the data. So that's all it is. Okay. So
you just call boundary effect somewhere where it makes better translate.
2 slides down. Actually, this is not a good test. It's an old one. It's easy to do, but it's no good for a number of reasons, one of which is the boundary effect. The boundary effects will come back in all the test statistics, but some of them are better at dealing with them than others. So this is the idea. Let's take an example. These are the same buffalo homicides that we saw in the nicer map earlier in the first lecture. This is a point map done in SPATStat. So the question is, are these points somehow more clustered than random or more regular than random? Obviously, just from looking at this, we're more interested in clustering because of this bunching in the middle. So how do we do this? We put a bunch of squares over here, and count in each of the squares how many points we have. So we have 40 squares, 8 vertically and 5 horizontally, and in each of these we count the number of events, so 6, 5, 1, and so on. So you see there are a few of these boxes here with a high number, 89, 45, 45. The question is, on average, remember, we're not looking for clusters. We're looking for an overall patterning. On average, is this serious enough to reject spatial randomness? So to get there, for each of the boxes, and this is something you can do in SpatStat, 14 is the average number, the expected number of points. 6 is the one we get. We take the difference. We square it. We divide it by 14 again, and that's this number. So you see, I mean, it's not that complicated. All of these are below average, so they have a minus contribution to the chi-square. But these here are above average, and some quite a bit. If you add it all up, the overall test is 960, 39 degrees of freedom. That's 40 minus 1, and this is clearly a rejection of complete spatial randomness. So it's very easy to do. You go smack a grid over there, count the numbers, compute the mean, and do the chi-square test, and we're done. However, how big should these squares be? How many squares? 40 or 80 or 20? Each of these will have an effect on the statistic. They're scalars. We talked a little bit about the modifiable areal unit problem in the first lecture. That's very much relevant here. Depending on how big or how many quadrats we have, we may have totally different conclusions. And the shape is also an issue. Should we take squares or rectangles or circles? A third issue is, should these locations be fixed or should they be random? In some of the early literature on quadrat counts, there were also test statistics based on randomly placing, say, 40 squares of unit area over the point pattern and then counting in those. Obviously, these counts are not independent counts, especially when we're interested in spatial patterns. We have to take into account spatial autocorrelation, in that the numbers in each of these cells will tend to be spatially correlated, and in that case, your classic chi-square test is invalid. So forget about it. This chi-square test is not, I mean, you can still, it's important maybe for me to step back. When I say it's invalid, what do I mean? I don't mean you can't do it, because you can count the events and compute the average and compute this number. Invalid means that this number does not follow the distribution that you think it does. So it does not correspond to a chi-square distribution with n-1 degrees of freedom. Maybe it has a thicker tail, maybe it has a thinner tail, maybe it's symmetric. You don't know necessarily which way it goes, but what you do know is that it doesn't follow what you think it does, and therefore, whatever p-value you come up with is not the proper probability of your type 1 error. That is, the probability that you reject the null when the null is in fact correct. That's what you want to have right. If you don't have that right, it's called a biased test, in that you draw the wrong conclusions too often. That's basically what it boils down to. So spatial autocorrelation will invalidate your chi-square distribution. Border effects also matter because of the spatial autocorrelation and because you don't know what happens outside the arbitrary. This is more an issue when you put the squares on the point pattern. When you get closer to the edges with random, as they're called, random locations for the quadrats, you can have them cut outside the fixed boundary of, say, a convex hull or a bounding box. And then you don't know what's happening out there. And we'll see that later on too when we do distance computations. As you get closer to the edge, you don't really know what's happening outside your bounding box. There may be points there or there may not be. the way you're counting it is which way? I mean, think of, let's go back here, and instead of putting a regular grid, I'm putting a random square on here. Let's say I put my random square as I draw it here in the upper left-hand corner. What's happening here in terms of my count of events per area? Okay. Here I have a count of events per area. All the events in my area, I have them all. Here, I only have the ones inside the bounding box. I'm implicitly assuming, at least in the naive way, that there are no points outside the bounding box. So I'm undercounting the number of events per area, which will give me a bias of the statistic. So then the corrections for this consist basically of two approaches. One is to sort of try to figure out or estimate what the number of events outside the bounding box might be. The other one is to artificially make sure that you never get outside the bounding box. And so you create a buffer zone. If you create an artificial buffer zone, say here, a rectangle inside the big bounding box, then your square, if it stays within, if the buffer is large enough, then your square will never reach outside the bounding box. Of course, as a result, you lose observations, because you lose the observations that are in the buffer. They're only counted when your square is outside the inner bounding box, but they're not counted in their own right. So we'll see these methods again when we look at distance-based statistics. So the upshot with Quadrat counts is very easy to do. It's a quick and dirty check, but a lot of caution is needed. They're typically misleading. I mean, that doesn't mean they're always misleading. In this case, they're not misleading because the clustering is so strong that whether you use a Quadrat count or one of these other methods, over and over again it comes out very strongly as rejecting the null hypothesis in favor of clustering. So in this case it doesn't matter that much. But when you get a p-value of 0.05 or 0.045, then it does matter. And then in most cases you should not rely on the Quadrat counts as